and the fixed point methods in this 2 week. Let me see. Okay, I got this one. So let me give you some introduction first, and so I'm going to take somebody's advice, and then I'm going to post a well-typed notes to the canvas, and so. But here, this is a handwritten one, and maybe you will find that there's some information in the handwritten one, and then there's some information that is not in the handwritten one, and then that it would be on the type notes. And so now let's see, what's the bisection method? So this time we are going to solve the numerical method. This is the numerical method for solving a linear equation, and first of all, we are going to focus on the one dimensions problem, which means that we are going to solve just the function, and then the variable is just the scalar variable. And so here, which means that we are going to consider to find the zeros. So what we are going to do is to consider solving or finding the zeros of the function fx, and which means that we are going to solve this fx equals to 0. And for examples, we are going to solve this. Let's say the function fx is just the exponential x and then minus x, and then we want to solve this. This is one example here. And first of all, we are going to take a look at a very simple but robust methods to solve this kind of problem. It's called bisections methods. And the bisections bisection method, and this is the first methods we are going to talk about in this class. And the bisections methods, which is based on, this one is based on the some things you are familiar with. It's based on the intermediate value theorem. So let's take a look at the intermediate value theorem. And so suppose we have a f function is continuous, and on the interval, let's say is on the interval AB, and with the FA and the FB, they have this opposite side. With FA and FB, they have the opposite side. And which also means that if you take a look at here, FA, FB have the opposite signs, and which also means that the FA times FB, the value is smaller than 0, right? Then the intermediate value theorem means that, implies that, okay, here we apply the intermediate value theorem here. The intermediate value theorem implies that there exists a point P, and then which is in the interval A and B, and then with the P equals to 0. Does it make sense? So this is just the intermediate value theorem, and then I'm going to draw the picture here in case that you have some difficulty to recall what we have in the intermediate value theorem. This is the interval A and B, and then now we have a function, and then the FA is above the FX maybe, and then the FB is below the x-axis here. And you can have definitely have a different function here, but here we have the FA and then FB, they have the opposite side. And this intermediate value theorem saying that there is this B here, and then such that the f function evaluate at this point, and that is just equal to 0. And what's this? At P equals to 0, and which means that the P is the solutions to the equations here, fx equals to 0. Does that make sense? So here the P is just a solution. And we need to say that I'm going to ask you a question. So let's say assume this function is continuous, and then the FA and FB, and they have the opposite side. And I have one question for you. Is that the solutions unique? No, why? Can you give me one example that is not unique? So you have continuous function and then opposite side, right? Oh, I can see someone is drawing.
Oh, what about like cosine?
Cosine, yes. So we can have some oscillating here. Oscillation here. Yeah, and then we have multiple roots here. Yeah, so there's one possibility that we have multiple roots here, but let's assume that so for this algorithm below, let's assume there's just one root, but actually you can solve for multiple roots. But at the end of the day, you are going to approach to one of the solution here. If with the bisections methods. So let's say we are going to approach to, I don't know whether which part is going to which solution is going to approximate, but actually it would give you one of the solutions here by the bisections method. So let's say, let's begin our algorithm. So to start off, and then I'm going to give you some picture here first. This is a picture. Okay. So I'm not going to do the paste here because the paste does not work between the MacBook and iPad. And then I'm going to draw the picture. So there's one picture here, and then I'm going to show you the bisections method process. And then let me give you one example. The example looks like this. So I have the x-axis, and then I got the y-axis, and I got my A interval, I got my B interval, and I also get my function, and then it's starting from here, and then it's going up, and here. Yeah, and this is the function. And so let's start off our iteration. And this is the bisection method. And this is the bisection method, the idea. And let's say we are beginning with the A and B interval, and then we give the name, give the A to be the A1, and then we are going to give them some index here, and then B is just a B1, and this is the A1, set the A1 and then to equals to A, and set the B1 to B, and now let the P1 here, and then it be the let the P1 here be the middle point, middle point of the A and B, which means that the P1 here is just the A1 plus the B1 and then divided by 2. And let's get that point here. And it's quite, this is a very bad example. We stop the iteration here. So, but that is one thing. So let's say, okay, this is the function. And if you find the middle point, and then there are several cases, right? And it could have the following cases. So case 1, and you have already seen the case 1 here. And that is this is the case 1, and we have the middle point of function, and then evaluate at the P1, and then it equals to 0. And then the solutions P, so we use the P to denote that is the solution. The solution P is just equals to P1, and then we can stop the iteration. We can stop the iteration. Stop iteration. And there's the other cases, and I'm going to draw another picture here. This is a very special case. We just stop at the first iteration, and then this is the function where the middle point equals to f evaluate at that point equals to 0. And there's other cases. Let's say there's another cases here, and let's take a look at this value. And this value here, the FP1 is positive. So there's a case 1, case 2, and then which means that FP1 is positive, right? And then this one is negative, and then the FP1 is positive. And so there's 2 cases. Either this point, the value at this point has the same sign of this one, and then or this value has the same sign of FP1. And so there are 2 cases here, and we have case 3. And there are 2 cases, either the FP1 and the FA1 has the same sign, have the same sign. Then if this happens, and then which means that if we take a look at here, we are not going to say have the same sign. We are going to focus on have the opposite side. Have the opposite side. And if you take a look at this pictures, and then actually this middle point have this opposite sign with the FA1, and you can see this. If this one has the opposite sign of this one with this one, and then the solution P is actually in this interval A1 and P1. So now, instead of letting the B1 to be the right endpoint of the interval, and then now we are going to set a new right endpoint of the interval, and that is the P1. Does that make sense? So because these 2 have this opposite sign, and then now we can confirm that the solutions P is inside this interval, this smaller interval, and then it's A1, P1. So now we are going to set a new interval, smaller interval, by resetting the right endpoint to be P1. So this is the things. So this is the case 2, and we said what we are going to do for this step or this case, and then we set the A2 to be our P, A2 to to be the A1 and the B2 to be the P1. And so this is the new interval here, A2, right? And then this one, it would be the P2 in this case. And we get a smaller interval to find our solution. And this is a smaller one. And then at the very first, and then we are working on this one. And then, but now we use the middle point and then to decide a smaller interval to find the solution. So there's another case. There's another case is that the FP1 and the FB1 have the opposite sign. And then we are going to do the opposite things. And if you have a function looks like this, let's say we have a green function. This is another function, fx. And when you get the middle point and then fp1 here, and then you will find out that the fp1 and the fb1 has the opposite sign. And now we can determine that the solution is located at a smaller interval, and then that smaller interval is P1 and B1 instead of the A1 and P1. So now for this case, we are going to reset the interval, looks like this. And then we set the interval A2 and then equals to the P1, and then the B2 equals to the P1. That's like B1. Does it make sense here? How to reset the interval for each iteration. So now you get a new A2, and then you get a new A2, and then, so this is B2. This is B2, not the, this is the new interval. I'm going to use the A index to indicate the left endpoint, and then B is the right endpoint. And so here, this is the new left endpoint here, new right endpoint for this function set x. And so you can continue to do the bisections process. For examples, on this interval, you will keep doing the bisections and then take the middle point. And then we are going to give the middle point, the notation is P2. And but here, if you take a look at the P2 and then this function at the nodal point at the middle point of this interval, and that is equals to 0, and then we will stop the iteration here. And if you have the opposite sign, and then you will keep doing the resetting of the interval here, and then we have case 2 and then case 3, and then we reset the interval, and then we get a half size of the interval here, and maybe this one, and then maybe it is this one. So you keep the iterations here, and then for the smaller interval, and then that's it. Any questions? Any questions here? So the bisections idea. The next part is to keep doing the iterations in the this green part. And then maybe you would get a smaller interval. And let me just perform the next part for you. Maybe give you a more better functions to demonstrate the idea. So let's say we have this function, and then now we already get the A2 and B2 there. So we already get the A2, B2, and now we are going to do the bisections. And then once again, we got the bisection and get the middle point. And then this is the middle point. The middle point of the A2 and B2. And then this is the middle point. And then we take the P2. And we evaluate these functions at the FP2. And this is FP2, right? And now we are going to compare the values at the FP2 this is FP2, and we compare the values at FA2, and we also compare the values at the right endpoint of this interval, that is the B2. This is the values at B2. And if you take a look at this three value, this one, and this one, and you will find out that this value have the opposite sign with this one. So now we are going to reset our intervals into this one as the left endpoint, and then this one is the right endpoint. And each time the left endpoint and right endpoint, they have this opposite sign for the value, the function value. And this is the new interval A3 and then B3. And so now we are going to reset our value. This is the A3, and then this is the B3, and then B3 equals to B2. And this is the new interval. We are going to try to find out our solutions of the fx. This is the new interval. Does it make sense now? One more iteration, and let's go. Let's go to the next part. And this is the whole idea. And then you would go to take a look at the textbook, and it includes the computer's algorithm, the pseudo algorithms on the lecture notes. And if you take a look at the algorithms on the lecture notes, and then you will see actually you just need 3 variables. You don't need a lot of variables to save your calculations here. So you don't need a lot of space to perform such a algorithm. You just need one variable to save your left endpoint, and then another variable to save your right endpoint, and then another variable to save your middle point. And that's it. And also you need to calculate the f functions, f values, and value at the endpoints and middle point here. But the storage of the number is just 3 points: left endpoint, right endpoint, and the middle point, and then that's it. And so if you take a look at the algorithms on the textbook, and then it's quite storage space saving. And now I'm going to give you one example here. There is another things I want to mention here. So in the algorithms, actually you have several things. You have the tolerance, and then you can decide. So in the algorithms, and then what is the input? Input, we have the I'm not going to write out the whole algorithm here, but what is the input? Input, we have the initials interval A and B. And you need to double check first, at the very first, your FA times FB, they are smaller than 0, or the FA value, the sign of the FA and the sign of FB, they are different. And this is the first input. And then also you have a stopping criterion, and then that stopping criterion, you need a tolerance number, and also the input is fx. And so there is, and what is the output? Output is just the approximations of the solution. And this is the output. And there's one thing that I want to mention here. So a lot of time you will find out that, for examples, you have the function. So there's one example here, and then I'm just going to illustrate the idea here. So for example, this fx equals to 2x cubic minus x squared, and then plus x minus 1. And if you text 2 interval, and then it could be f-4 and f4, and then it's smaller than 0. And you have f0 and then f1 and then smaller than 0. Which one would you choose to be your input A and B here? Actually, I would choose the later one. So I have two intervals, right? -4 and 4. And then I have another choice is 0 and 1. And which one I would use to be on my input here? So I would use this one because this one I have a smaller interval to begin with. And then it also satisfies this condition here. So I would rather to try this one because this one, the interval is smaller than this one. So each time if you have different interval and then they all both satisfy these conditions, the products or the sign of the value here, they are opposite. And then I would choose the smaller interval to start off here. And so I would prefer this one. And that's it. That's it. Any question here? Because if you take a look at here, it could like if you want to do the bisections process here, and then it would probably goes to here. It would probably goes to -4, and then do the bisection. It probably goes to 0 and 4, and then it would probably goes to another interval, and then that is 0 to 2, and then it would goes to 0 to 1. So if you just start with the 0 and 1, and then it takes you some time to get the solutions. And you can do you can reduce the number of the iterations by 3 here. And so I would choose a smaller interval here. That is something I want to put the remark here about the input and output. And then for the tolerance number, I'm not going to, the tolerance or stopping criterion, I'm not going to talk about some things today because I cannot show you the entire algorithm here from the textbooks by some technical problem between the iPad and MacBook. But today, let us just focus on some examples that we can understand the bisection methods. So let's say, so first we need to show that the fx equals to x cubic and then plus the 4x squared and then minus the 10 and equals to 0 and has a root. So first you need to show that we have a root on the interval 1 and 2. And second, and then we are going to use the bisections methods. The bisections method to get to approximate the solutions to approximate the root with the error less than 10 - 4. And so if you want to show the first things, and then what would you do? You are going to apply the intermediate value theorem to here, and then to see what we have. So first, you will show, let's evaluate the function at the 1. So that is the left endpoint. And then let us also evaluate the functions at the right endpoint. And at the end, if you do the plotting with your calculator, and then f1 is just equals to -5, and then f2 equals to 40, and the intermediate value theorem. So here we have f1 and then times f2, and that is smaller than 0. And this means that this means that they have the opposite sign, and then the intermediate value theorem gives us that the intermediate value theorem implies that so implies that we have a root in the intervals A and B, and that is the 1 and 2 here. And so we finished the first questions, and now let us use the bisection methods to do the to approximate the root. So first of all, we get the P1, and then it equals to the 1 plus 2 divided by 2, and now this is just a 1.5. And we evaluate the function f at 1.5, and then we get, what is the value of this one? It's the 2.375 by the calculator, and which is bigger than 0. And now we want to choose the point. So let me just draw the picture here. And this is 1, and this is 2, and this is 1.5. And at the very beginning, and then this one is negative with the negative sign, and this one is with the positive sign. And now I get a positive sign for this middle value. So now I'm going to choose the opposite sign here, and then which means that I choose this to be my left endpoint, and this one is the right endpoint for the next iteration. And so now we have because the F1 and then F1.5, they have the opposite sign. And I am going to set the A2 and then equals to 1, and then my B2 equals to 1.5. And this is my new interval for the search of the root of the function. And now I'm going to get my P2, and then P2 is just the 1 plus 1.5 divided by 2. And I got this value, it should be 1.25. And this is my new midpoint, and then 1.25. And I am going to evaluate this function at 1.25. And this value is just negative 1.796875. And which means that I have negative sign for this middle point here. And I'm going to choose, something that is different from the negative side to be the other input. So here, that is this one, this point here. This is negative sign, this is positive sign. So here, this is the new interval for the next search of the roots. And so this is a new interval, and I'm going to set, okay, because the f1.25 and then times the 1.5, this is just saying they have the opposite sign, and then my A3 equals to 1.25 and B3 is just 1.5. And you can keep doing such and such here, and there is some stopping criterion here you can use. That is to use, let me see, you can use this one. So you can use the stopping criterion here. And this is the Bn, and minus the An, and then divided by the An, or minimum of the An and Bn. And then when it is smaller than the tolerance number, what is the tolerance number here? It's less than the 10⁻⁴, and then we can stop there. So if you take a look at the lecture notes or the textbook, and actually the iteration stop at the B13. So actually it gives you the P13, and then it's the accurate solution, it's the acceptable solutions. And then the P13 is equals to the 1.365 and then 112.305 here. So why this stopping criterion looks like this? You can have other stopping criterions, but why does this stopping criterion indicate that the solutions, the area of the solution is less than this number? So I'm going to show you this one. If the Bn and the An satisfy such an condition here, then the area of the solutions was smaller than the 10⁻⁴. So this is because, and remember that we have the notations for the solution. The true solution is P. This is, let's say this is the true solution. And the error here, it means the relative error. This one is the relative error. And let's say this is the true solution, and then what's the relative errors? The P13 is the desired result from the computer programming result. And the relative error, it looks like this. It's just the error, the difference between the true solution and the approximation solution, and then divided up by the P. And because, so let's say this is the solution. This is the P13. And then this is the P13. Let's say this is P13. And this is the interval. And then this is the interval A14. And then this is the B14. This is the iteration number. And if you take a look at here, the true solution, it could locate at between the A14 and B14, and that P is also in this interval, which means that the difference between the P and the P13 is less than the length or the interval here, the A14 and B14 interval. And so, which means that we have these things. So, which means that we have this length, the difference between the true solutions and the approximation solution is in between the interval A14 and then B14 here. And for the true solution, actually we can have, so the true solution here is located at here. And which means that the true solutions is actually the absolute value of the true solution can be bigger than the minimum of the absolute value of the endpoints here. So I'm going to bound it with the minimum of the endpoint here, the minimum of the endpoint A14, and the minimum B14 here. And it happens that because it is positive, and then the minimum is just the A14 for this example. So here we have is just the A14. It's just the, if this one is smaller than the 10⁻⁴, then the relative error is smaller than the 10⁻⁴. Does it make sense? So we don't know the true solution, but we can use this as the criterion to stop our iteration, because this is the relative error, and then this relative error is smaller than this stopping criterion. And then when the stopping criterion is satisfied, this criteria here is smaller than the 10 - 4, and then we can stop the iteration, and then we know that the relative error of the solution is smaller than that one. Does it make sense? Let me see. Do we miss something here? Not really. I think that's the same. And this is one of the stopping criterion, and there's other stopping criterion here, but you can take a look at the textbook. Sometimes people would use different stopping criterions. You can take a look at the stopping criterion to think about why do they have such a stopping criterion, but I'm not going to explain it. People would choose the proper stopping criterion for their approximation, and then there's different stopping criteria here, and then sometimes people just take a look at the difference between two middle points, and then when they are the difference between two middle points are smaller enough, and they stop. And there's another stopping criterion there, and then that is the relative error between the relative difference between the middle points. And I'm going to use a P to indicate P, and then subscript here to indicate the difference middle points from different iterations. First of all, the Pn does not equal to 0. Otherwise, we get the solutions, right? And am I right? Not really, because we require that the Pn, the denominator here, does not equal to 0. So we require the Pn does not equal 0 here. And there's another stopping criterion, and this is the residue of the equation, and this is the f, and then you evaluate at Pn, and then which is smaller than epsilon. If you compare these three stopping criterion, and then this is easy. The left-hand side here is easy to calculate because you just need to do the difference and then subtraction between two numbers, right? But this one is the best stopping criterion because you can see how much difference between the fx equals 0. So here, this is just a residue, right? Because we are going to solve fx equals to 0. And then you are expecting that if you put in the approximations number and then Fpn, and then it's approximately equal to 0. So if you just put in the Fpn here, and then which means that you are estimating how far is this one, how much. So then let's see how far is the equation here, and then the difference between this one and this one. So this one is the best one, the best criterion to estimate how far we can get to here. But here, the problem of this one is that sometimes the f function is quite complicated, and then it takes the time to do the plotting here. This things is easy to calculate, to compute in the computer, and then but this one is the best stopping criterion, but it's it takes a lot of computational cost to do the plotting here. So people sometimes would choose this too, other than this one. Although it's the best criterion. And so now let's take a look when let's discuss this one last time. We're going to see the convergence rates for this bisections methods, and next time you will see this convergence rate is related to the iterations number, and that iteration number is So let's say we have n iteration, and then the convergence rate is the order. So it's the big O and then 1/2n. And then this is the convergence rate. And then we are going to prove this next time. And you need to know your proof for the final exam because it's easy. And I will keep the things to the next time. And then this class is over. And I'm going to let you go. And next time we are going to talk about the fixed point method as well. And if you want to preview the class a little bit, and then you can go to take a look at the textbooks fixed point methods.
Thank you.
Bye-bye. I'm still using that first textbook for the second part of the course. The first textbook, that is the blue one. What is going